right? Like the intersection. We need to remove it. But each time we remove it, we need to add things back, right? Because each one would have the intersection the trinary intersections, right? Each time we remove it, we need to put it back. So if we remove this, there's a trinary intersection and there's a quaternary intersection. So if I remove it, I need to add one back. If I remove it, I need to add one back. If I remove it, I need to add one back. If I remove it, I need to add one back. So there's 4. But why do I need to add this?
Because that's also part of the
Right.
intersection.
But why do I only need to add 2? Actually, I need to add 3, not 2. Because I need to leave one behind. The format looks like this. Notice that I removed 3, but then I just only added 2 back. You can verify. We can verify actually. We just need to do the process I did a while ago. So we will try to do that, to verify it. But I tell you that this thing follows this format. So if we go 5, which, can you draw 5? Maybe not. We already have trouble with the 4, so maybe 12. How would it look like a bacteria now, maybe? Oh, not a bacteria. Bacteria is only 4. You can ask a question about this if you like. But go ahead. Send any comment on 4 and 3 and all these minuses and this 1 here. It's really hard to look at it here, really. Alright, so anyway, I will give you a copy of the derivation of this based on that drawing, so you can check it out. So for now, we all agree that this thing works out, but we need to see the proof. Is there any book that discusses this that you know of? Not yet. So we will try to make our own derivation of this, showing all the colors in a much clearer sense. Not you, but I'll do it.
And published it.
And I'll also show a derivation coming from this drawing. No? Let's erase it now. So let's save that equation. What's my eraser? On that. Then 2 is not really, there's no intersection between what happens before.
There's no intersection.
What I mean is, let's make it simpler for us. Let's just go back to 3 events. Mickey Mouse. A formula a while ago for at most 1 for 3 events was 1 minus P E1 intersection E2 minus P E2 intersection E3 minus P E3 intersection E1 plus 2 intersection E1, E2, E3. Alright, but now it's a different situation. There is no intersection between E1 and E2. Which one drops out? Now obviously this one becomes 0. There is no intersection between them. E2 and E3 exist. Obviously it's right there. E3 and E1 exist. Does this exist? Make things easier. does it make sense that at most one is just everything except this and that? Yeah, does make sense, right? Most one. This is most one, 0, most one, and most one. It does make sense. What if all of them doesn't have any intersection? Just one, of course. Everything becomes 0 here. And at most one is everything. What do we call this kind of events? Mutually exclusive events. Is that the same as is it the same as dependent events? Or in that case, independent events? Is it the same? No, it's not. No, it's not. But some books actually say it's the same, but it's not. So we know what this thing is. This means if they're mutually exclusive events, if I talk about E1 and E2, then the probability of their intersection is 0. That is a mutually exclusive events. But when events are independent, we talk about this. You encounter that? It's a probability of B given A. And if that is 0, then that is an independent event. So it's two different things. This is not equal to that. This is different. But sometimes they become the same, and we will see that. When does this become equal to that? But anyway, for today, we'll just end up with mutually exclusive events, and I'll give you one last problem before we end, where we talk about exclusive and mutually exclusive events. And later on, put that in your mind, because we're gonna relate this to the t-test and how it is related to the t-test, mutually exclusive and exclusive, non-exclusive events. Okay, so I'll write down the problem that we will do. So just go back to your old Venn diagram that you did a while ago. But there's just an additional questions I want to ask. So I would, are you done copying this? No? Sure.
We're just talking about the schedule for Saturday. I'm sorry for interrupting.
Ah, yeah, sure. No problem.
Is it still possible?
What time, if ever you can arrive, but you cannot. Just, it's not really a problem, possible. The amount of French students from 10 becomes 9. And also thus the universe itself, because you already removed it from itself. That would be 9/29. But the idea of getting the probability based on this analysis would be multiplying the two. But that's what we wanted to understand. Why do we try and multiply the two together? The answer to this is basically 10 over 30 times 9 over 29. We do understand that 10 over 30 is what we did a while ago. We understand that 9 over 29 is what we did a while ago. But why do we multiply? But that's the answer. If you're not going to ask why we multiply it, that's as easy as answering it. If I even ask you to do a third student, so that would just be 8, because there's like 9 before you get another student, it would be 8 thirds. Third students over 28. So that would just be multiplying it again. If I do a fourth student, well, it's just the same thing. Seven over 27. And it seems to be reminiscent of 10 times 9 times 8 times 7. Looks like a factorial, but not entirely like a factorial. It's equal to 10 factorial over 6 factorial. But we will not go into that yet. Okay, but this is the trend that we're looking at. And this shows to you that these events are actually dependent. These are dependent events because the probability changes. And that's what we're going to study next time. Dependent events. Probability of dependent events. If I said that there was with replacement, it means that if I got one student, I will bring it back to the group. That only means that the French students will still be 10 and the universal set will still be 30. So the answer to that is if it was independent, and this is dependent events. Ten over 30. What is this? 10 over 30 still. 10 over 30. And 10 over 30. So it doesn't change. But what we wanted to find out is why it is multiplied. It is related to the definition of this, and we will find out how that is defined in Python. Do you have any idea of how this thing is defined? How is it defined?
It's probability of B intersection.
Sorry?
Defined as in
Yeah, like
A
how,
intersection B
yeah, A intersection B.
over the probability of A.
Oh. That's nice. Alright, so that's correct. And how do you define this in terms of what we did? Number of an intersection over view. And what happens to that mathematically is it cancels out. And we get n A intersection B over. Now I want you to look at this in a Venn diagram so you can internalize it a bit more. I'm just going to give you a sneak peek of what Saturday would look like. Oh. So we said that the probability of A given B, B given A, is equal to this. I did the mathematics. It turns out to be just the number of the intersection over the number of A. So let us find out. Here's the intersection of A and B. And what this thing is telling me is just basically this divided by that. And this thing, of course, represents how many is inside. How does that translate in English to you guys? It's somehow trying to find the part of B, right? It's a part of B that is found on A. Right? The probability now kind of tells you that it only takes the part where B exists, given that A exists. So this thing is taken as its whole now, instead of the entire universe. As you can see, it's not U anymore, right? It's just taking this part where it exists, because it doesn't exist outside. The B doesn't exist outside. It only exists in here. But why are we not taking this part? Because it's saying given A, right? Given A. We need to take where B exists, also where A is defined. Right? That makes sense a bit. So that's what it means by the probability of B given A. Or in other terms, the probability of B where A exists. But how is that related to this multiplication? It's easy. You just need to rearrange this equation and put PA on the other side. I start drawing the circles. Let's be a mathematician someday. Alright, so let's see now we have P. Oh, I always get that. The probability of me getting this is really high.
Yeah.
Separate that. Although there's only, like, what's the probability of me getting this? I just want to ask. It's 1/4, but why do I keep getting it? It's 1/4, but the probability becomes higher because everyone chooses that. It becomes 1/2. Right. See, I choose it again. So I have that. So I want to ask something. How is this different from that? Maybe by now you can say that in words. The intersection and this. Well, we can just define it so we understand. This is this, right? And this is this. Almost similar, but the difference is what we're taking note as the total. And that allows you to think, how is the intersection different from PBA? But does it become the same? Does it become the same? It becomes the same only if is that possible? That NA becomes NU? What I'm trying to ask is, does the intersection become similar to PBA? Yes, it can happen, only if and only if, NA is equal to NU. Question is there a possibility that can happen? We know it would be equal if this thing happens, but my question is that going to happen? Right, it does happen, right? Yeah. It does happen. Can you give me a set that is already the universal set? In terms of numbers. Who is the universal set of all numbers? It's a complex, right? The complex is a set of numbers which is also the universal set of all numbers. Is that correct? Do you agree that the complex number is the universal set of all numbers? It's also just a set. So and that's the case where the universal set becomes just a set. And that's also the case where this becomes that. Because now NA is equal to NA. And these two things become equal. And remember what I told you a while ago. What's the difference between dependent and mutually exclusive? Mutually exclusive is when this is zero. Independent is when this is zero. Right now, they are different, right? But when these two things become the same, NA and NU, they now become the same, and then the definition of dependent and exclusive also becomes the same. So that's the instance where not two things become the same. That's why books sometimes use the two terms interchangeably. Because there's an instance where it becomes the same. It's 9 o'clock. Right. We're all like bored. Oh, we can go. So let's just stop there. This is answering the question I was posting a while ago. So let's stop here. Let's continue now. 1, 7.